Yeah. It is supposed to be recording now, I think.
I can see it is, yes.
Yeah. Okay. So just to introduce things, so in the Galala University, with the directions and consideration from the GU President, Dr. Ashraf Haider, and the Vice Presidents, Dr. Tariq Abou-Saleh and Dr. Mohammed Al-Shinawi, we are all aiming to introduce new fields and sciences and technologies to our students. And this is actually to increase their knowledge and widen their vision. And this is why I'm having this sort of series of seminars specifically directed toward nanotechnology and, microfluidics and, micro and nanoscale region and field. And this is more to introduce this knowledge and raise awareness about all of it. This year we are having our first cohort of students going toward nanotechnology program. And one of the things that all students keep asking about is what are the application of nanotechnology, field works, and so on. And this is why I started to arrange this series to increase knowledge and raise awareness about it. So we are happy to have you with us as a speaker to introduce microfluidics. I know you are the expert. And to say a very important note about this, cell is actually one of the very good models showing the change and the multidisciplinarity in science, because I think, Sal, you graduated as a chemist.
Yes,
correct?
I did, yeah.
Chemistry, your main or major was chemistry.
Yeah.
And then you started working in microfluidics within your PhD, chemistry side. And then when you started working with us, it was about, or when we started working together, it was about drug delivery using microfluidics as well. And then we started to, or you specifically started with your group to go toward the organoids and spheroids and growing cells and chips. So you have been moving through different fields, and this is showing how multidisciplinary and science is, which is amazing. So I was trying to also let all students know that there is the modern trend at the meantime is actually to go between different fields of science, to be multidisciplinary. It's not like I'm a chemist or I'm a physicist or whatever, like a very specific field. So I'm trying to have a look first of all to see if we have any of our vice presidents with us at the meantime. Yeah, Dr. Tariq is here with us at the meantime. Would you like to introduce Sal, Dr. Tariq, or would you like to speak with us?
Yeah, good evening. Good evening, Dr. Radwa, and thank you very much for arranging this webinar. Hi, Sal.
Hi.
So happy to have you with us today. As Dr. Radwa said before, we aim to organize such webinar, taking a good chance of the lockdown and all the world. So I guess we all have some time to share knowledge and recent technology between us. Of course, students as well are now in holiday in Egypt, so they have a chance to listen to eminent professors like you. I guess this is maybe the second seminar in nanotechnology that Dr. was able to organize. And the subject, I am a chemist myself, so I would be very interested in your talk about fluidics. So thank you again, and next time maybe we have a chance to meet you face to face in Galala.
That would be nice. Thank you very much.
Okay, I guess it's all yours now, Sal, so you can share your screen and start. I will switch my video off, so I will give you all the, just to keep my internet safe.
Yeah, that's fine, that's fine.
Okay.
Okay, can somebody let me know if they can see my slides and if they can hear me okay?
It's all right, Sal. Yeah, everything's okay.
Okay, so good afternoon, everyone, or maybe good morning to you all. First of all, thank you very much for this invite. It's really a nice part of my job being able to speak to new audiences, particularly about the type of science that I feel very passionate about. And Radwa is absolutely correct that I started life as a chemist. I did my PhD in chemistry in developing microfluidic devices for analytical chemistry. And then since that, my PhD, my journey has taken me to physics. So now I work in a physics department and I lecture in physics in nanotechnology. But my research is very much based around cancer biology, so cancer research. So I really have spanned chemistry, physics, and biology so far in my career. And, we're absolutely right that it's multidisciplinary research that is really driving some of the biggest advancements in our in our science today. So I'm a big advocate of crossing those boundaries. So today we're going to talk about my area of
Sal, are you still here with us? I'm not sure if this is only dropped from my side or.
No, I can hear you, Dr. Radwa. However,
yeah, I think it's very weird if it is from Sal's side. Let me try and check with her now.
So I guess we combine everywhere, not only in Egypt.
I think it's
from
she's not with us.
It's from Sally's side.
It's from her side, yeah.
No, from me. Maybe she has power cut.
power cut in UK.
even it's a heavy rain, and we're expecting a power cut here in Mansoura.
Yeah, it's raining in Cairo, close to the Cairo airport, just a little bit, and then it stopped now.
Yeah, it's.
I haven't received anything back from Sal yet, guys. I'm really sorry. I will stop the recording now anyway till we can receive anything. Here she is. Hi, Sal.
Hiya.
What's going on?
I've just been lecturing, obviously, to nobody.
Oh,
Sorry
really?
about that. I had no idea that Teams had thrown me out.
Okay. I thought you have power cut or something, which would be really weird, but okay.
Yeah, no, it didn't change for me at all. So
right. So you have been lecturing to yourself all that time.
yeah.
Great.
That's
we'll
fine.
start
It means
again.
that I know exactly how to start the lecture. So
Right.
and my phone was
Okay.
of course on silent. So here we go. Let's try
Okay.
that.
Right. Okay.
Can everybody see this?
Yeah, it's clear now.
Excellent. I can't remember at what point it glitched out, so I'll just get straight into the actual lecture. So we'll go through the concepts of miniaturization, so why we do microfluidics, and the advantages of miniaturizing basically analytical and synthetic science. The theory of microfluidics, so a little bit on the motion of fluids and something called the Reynolds number, which is an important parameter in microfluidics, resistance and flow in fluidic devices, and also a little bit about diffusion. And then we'll talk very briefly, but to give you an idea of how we actually make these devices and how we design them for specific tasks as well. And then I'd like to talk just very briefly about the applications of microfluidics, two of the main general applications of microfluidics, but then move on to some of the research, specific research that we're doing at Leeds that is underpinned by using microfluidics. And in fact, we would not be able to achieve it if it weren't for not having microfluidic devices. So miniaturization. So the microfluidics is about the miniaturization of fluidic processes onto something the size of a microchip. And this is synonymous with the miniaturization of the electronics industry. So when microelectronics were developed, it improved many aspects of electrical circuits and electronics. And the same as for microfluidics, it's the miniaturization of benchtop systems. So these sort of big flasks that we do reactions in the laboratory that have several milliliters or liters of volumes of liquid, and moving them onto something much smaller to basically improve what we're doing. And the same for some of the instruments that are based around fluidics. So this is an HPLC machine for doing analytical science. We can miniaturize it down onto something the size of a microscope slide, basically. So microfluidics is a network of channels that have been fabricated into a solid substrate. And the channels, importantly, are micron-sized in depth. Oh, sorry about that. Micron-sized in depth and width, and can be up to several centimeters long. But the critical dimensions in the depth and the width, so the cross section of those channels, is in the micron range. And we can flow fluid down there and perform chemical and biochemical reactions inside the microchannels. And there are several advantages of doing that compared to on the large scale that you see here. Okay, so some of the advantages are it improves reaction efficiency, and this is all to do with the amount of reagents you need to perform a typical reaction. So if you're doing something like synthetic chemistry, you tend to be able to get much higher yields by performing these reactions in microfluidic channels than you would do in a big round bottom flask. It decreases reaction time, and this is linked to the idea of diffusion that we'll go through in a few slides' time. Because of the internal volume of these microchannels, you're reducing reagent consumption. You don't need as much reagents to do the reactions as you do on the large scale. And of course, this reduces waste production as well, which is critical if you're producing toxic or radioactive waste. This, of course, makes the whole efficiency better, but it also makes it cheaper because you're not using as much reagents. And of course, the idea is that if you can miniaturize it down, like this HPLC machine that you've got here, onto something that's handheld, then you can ultimately make it portable. And that really revolutionizes how you might do analytical science. So instead of sending samples to a laboratory, you can take your laboratory to the site that what you're trying to do your sampling. So microfluidics has applications in point-of-care diagnostics. So this is the idea that instead of taking a blood sample from a patient bedside, sealing it, sending it over to a laboratory, waiting several days for the analysis to be done, then a report is sent back to the doctor and the doctor has to come and find you and tell you the results. Point-of-care diagnostics is the idea that you would take a handheld device to the patient bedside and do the analysis on their blood, just a pinprick of blood there and then, and get a result out in a few minutes rather than waiting several days. And this leads into the idea of personalized medicine. So if you can get a diagnosis quicker, you can prescribe the right medicine quicker as well. It also has a big impact in on-site analysis. So this includes environmental analysis. So instead of taking a soil or a water sample from a mountain, having to take it all the way back to the laboratory to do your analysis, and then realizing that you want to actually take another sample 2 meters upstream and have to go back out again. If you can do the analysis in situ on the mountain using a microfluidic device, then it saves a lot of time. And forensic science actually is a huge investor in microfluidic devices, because conventionally, when you're doing forensic analysis at a scene of crime, you have to package up the evidence and send it to a forensic laboratory. And the amount of people that handle that evidence is called the chain of evidence, and that can put weakness in court for evidence. So if more people have handled it, then there's more chance that it's been contaminated or it's got mixed up with other samples. Whereas if you can do your point of analysis at the scene of crime, then it strengthens that evidence and reduces any contamination. And then chemical, as I've already said, and material synthesis, you tend to get much better efficiency and much higher yields when you do these type of synthetic processes in a microfluidic device. So the idea is, if any of you are familiar with Star Trek, and Spock goes out to the new planets with something that he holds in his hand, and he analyzes the environment and he gets a readout there and then. So whoever made Star Trek all those years ago was already thinking along the lines of microfluidics. Okay, so we'll talk a little bit about fluid motion, because it is important. Don't worry, you don't have to be an expert in fluid dynamics to understand this, hopefully. So we just have to remember that a fluid is a substance that will deform continuously under shear stress. At the microscale and above, fluid is described as a continuum. So we're not interested in the fluctuations of individual molecules. We are going to consider it as a continuum. If you go down to nanofluidics, which is a field that exists, then we get down to the length scale that you do consider the mass and the momentum of each individual water molecule, but then it becomes a molecular dynamics problem. So what we're interested in is the continuum model, and the motion is described by the Navier-Stokes equations. And it does boil down just to force equals mass times acceleration. But in the Navier-Stokes, we consider various elements of the fluid. So we consider its acceleration, its inertia, but we also consider the pressure, the internal pressure of that fluid, the viscous forces associated with that fluid, and any external force that the fluid is experiencing. So they're the important parameters that we need to know from fluid dynamics for microfluidics, but we don't need to know it any further than that. So how does fluid behave on the microscale? One important parameter is something called the Reynolds number. It's a dimensionless quantity, which is the ratio of inertial forces over viscous forces. So if we look back at our Navier-Stokes equation and we take the component that is for acceleration and inertia and the component that is for viscous forces, and we make X our length scale L, then we can look at the ratio of these two forces over each other. And that gives us an equation called the Reynolds number equation, which allows us to estimate the Reynolds number for a particular liquid, depending on that length scale L and the viscosity of the fluid and its velocity. Okay, so the Reynolds number can be used to describe how flow behaves. On large length scales, the Reynolds number tends to be large, so anything greater than 4,000, we say that the inertial forces dominate over the viscous forces, and this gives rise to turbulent flow. When the Reynolds number is small, so generally less than 2,000, then the viscous forces dominate over inertial forces, and we get laminar flow. And we'll go into that in a little bit more detail. But just to put that into perspective, the Reynolds number for a typical microchannel is usually less than 1. So we're very much in the laminar flow regime in microfluidics. So we can predict fluid behavior in a pipe or a microchannel using that Reynolds number. And just to kind of visualize what we mean by turbulent or laminar flow. So turbulent flow, high Reynolds number situations, the molecules tend to flow in different directions. They are moving at different velocities and they are chaotic in nature. If we have laminar flow, what generally happens is that molecules are moving in the same direction. They're relatively the same velocity, though you do get this parabolic flow profile that you can see in the channel here. And because we know how fast it's moving and in what direction it's moving, then it tends to become predictable. So we know exactly where it's going to be at whatever time it's going to be there. And then just looking back at those Navier-Stokes equations, then we lose that, or that inertial term becomes negligible, and what we get is Stokes flow or creeping flow, which is an area of fluid dynamics that people usually specialize in. Okay, so the Reynolds number for microchannels, though, has to consider the fact that microchannels are very rarely actually a pipe with a cylindrical geometry. What they usually are a rectangle in cross section. So we have to make a very small adaptation to the Reynolds number to be able to predict how that behaves in a microfluidic channel. And it's just by considering the hydraulic diameter of that microchannel rather than just a circular radius. So we can calculate the Reynolds number for a typical microchannel. So if we take something that is in the width of 200 micrometers and a height or depth, the same thing, of 25 micrometers and a typical length of 5 millimeters, and we have to apply linear velocity, then we can calculate the Reynolds number for that type of channel would be 0.44, so well below the crossover between them. So that is in a laminar flow regime. So microfluidics is concerned with flow down channels in the order of micrometers. How do we make the fluid flow? Well, you have to have a pressure differential across the pipe or the microchannel in order to make the fluid flow. And flow is generated by positive or negative pressure at the inlet or the outlet of one of these devices. And that's what creates the pressure differential. So the inlet will have a high pressure and the outlet will have a low pressure. And just like in electrical circuits, that drives the fluid down the channel. But we have to consider various things when we're designing these microfluidic devices. And one of those things, just taking a step back, this is usually described by the Hagen-Purcell flow. And you can calculate pressure drops for an incompressible fluid or a Newtonian fluid in a laminar flow regime. And this is consistent. This is only if it's across a constant cross section. So we can calculate the hydraulic resistance and then the pressure drop for a typical pipe using these very standard equations. And the pressure drop is related to the hydraulic resistance of that pipe, which is also related to its length and its radius. And also the volumetric flow rate of what you're trying to push down there, so the fluid that you're trying to push down there. So the pressure drop can be calculated, or the pressure along that pipe can be calculated using these parameters. So for a typical, if we're talking about on the macro scale, a 10 millimeter pipe with a diameter of 1 millimeter and a flow rate of 1 milliliter per minute, so quite large compared to what we're interested in with microfluidics, you'd have a pressure drop to sustain that volumetric flow rate of about 7 pascals across that device. If we were to change the dimensions very slightly, so 100 micrometers at a flow rate of 100 microliters per minute, so we're reducing those down, but we've still got the same length on the pipe, then what we find is the pressure needed to push the fluid down becomes much higher. We're talking about 7 kilopascals now. So this is just an idea of how these geometries affect the flow in these microfluidic devices. But again, fluidic channels are rarely circular. They're usually in a cross section. So we have to make a few adaptations to those equations to take into account that geometry. So the hydraulic resistance equation looks very different for something that is got a rectangular cross section where the width is much higher than the height of the channel. So just in, if you are interested and you go into this, you just have to consider that the geometry affects the flow very, very much. So for a typical rectangular channel of 200 micrometers wide and a height of 25 micrometers and a length of 5 millimeters, then we would have a hydraulic resistance of 10 to the 9 pascal second per meters cubed. Okay. Does any of this sound familiar? So this is I always use with my students as an easier way to remember the relationship between flow rate, hydraulic resistance, and pressure differentials. It's because it's very, very similar if you consider Ohm's law on electrical circuits. So if you think, and in fact, the way we design microfluidic devices, so you can see this microfluidic device on your left, this looks like an electrical circuit, but it's not. It's a circuit of microchannels, but it is very, very similar to when you do look at an electrical circuit or a microelectronics board. And actually, the theory is identical between them. So if you consider both of them in electrical circuits, that we have a flow of electrons, they move along wires, they have a current, and that is driven by a voltage drop or a voltage differential, and we have electrical resistance, and this sits quite nicely within Ohm's law. In terms of microfluidics, we have the flow of molecules, usually water, but not always, and they flow along microchannels. Their volumetric flow rate is similar to electrical current. We have a pressure drop that drives that fluid, which is similar to the voltage drop, and we have a hydraulic resistance. And this is the Hagen-Sells law, which is very similar to Ohm's law. So we can imagine our fluidic circuits as electrical circuits and apply those equations and that theory, and that's what helps us design these microfluidic devices. The other thing I said was very important is the idea of diffusion in microfluidics, because in chaotic flow, in that turbulent flow that you saw, inertia mixes fluids together. So the formation of eddies and different currents moving in different directions is what mixes fluids together. In microchannels, we don't have high inertia, so things mix together by diffusion only. And most people say, hang on a minute, isn't diffusion very slow? And that is correct, but actually what you have is reduced distances. So diffusion itself, the rate of diffusion doesn't change, but the distance that something has to diffuse does. It's much shorter. So reactants tend to mix together more quickly. If you consider a microtiter well, so this is a typical volume of fluid we might use in biology, and it generally has a diameter of about 6.5 millimeters. And then we consider a microchannel, again, typically about 200 micrometers in width. And we put our molecules in there, and what we want them to do is be able to find the side of the channel and react, the green reactant to react with the purple one. And there's no other mixing apart from diffusion in these model systems. So we can calculate the time it takes to diffuse a certain distance using this diffusion equation. So X is your distance and D is your diffusivity. So that's naturally how quickly a molecule diffuses. And we've got distances of 3.2 millimeters for the microtiter well and only 100 micrometers for the microchannel. The diffusion coefficient for a small molecule, like a dye molecule, is about 10 to the minus 11 meters squared per second. So very, very slow. It doesn't travel very far very quickly. However, if you look at the microtiter well, if you were not mixing by any other means, only by diffusion, then this would take about 97 hours for that molecule to diffuse to the side of that well. For a microchannel to travel 100 micrometers, we're only talking 83 seconds. So you can see instantly how much quicker it is to do reactions in a microchannel. And this is nothing to do with the rate of reaction, it's just the dimensions of that channel mean that things mix much quicker. Okay, so how do we make microfluidic devices? So the common substrates or the common materials that microfluidic devices are made out of are hard materials such as glass, quartz or silicon, or polymers such as something called PDMS, which is polydimethyl siloxane, which is probably the most common microfluidic material out there. Harder plastics like PMMA and polycarbonate, And what you can see on the left here is glass devices, so very rigid devices. And then on your left is a typical cast of a PDMS device. It's a soft polymer. It's very flexible. And you would choose the material of your microfluidic device depending on what you actually want to achieve, what you want to apply your microfluidic device to. The fabrication, the way you fabricate, depends on the material substrate. So if it's a hard material like glass or silicon, you tend to do wet etching or deep reactive ion etching. And then photolithography, injection molding, hot embossing tend to be for polymers. So these are actually much easier techniques than wet etching or reactive ion etching. And the substrate material and fabrication choice depends on the application and or the cost. So for instance, glass devices tend to be very expensive because you use a device over and over again, but you can also, because it's rigid and it's chemically inert, you can do lots of organic synthesis in there. You can put harsh material down there and it won't affect your device. PDMS, on the other hand, is very cheap to make, and you can use one device and throw it away, but it's not very chemically resistant. It's not very resistant to pressure. So you tend to be much more restrictive as to what you can put through a PDMS device. So you have to really choose your material depending on your application. We're also moving into 3D printing microfluidic devices, which is new, but it's very exciting because most microfluidic devices are planar. They're just on a 2D system. But if we can 3D print microfluidic devices, then we can have channels in the Z direction as well as the XY direction. So this is very new, but it's going to, I think, revolutionize the way we make these devices. So it's very exciting as well. And also the idea that you can print biomaterials, so be able to print microfluidic devices that contain cells and biomaterials such as collagen and fibronectin and things like that. Okay, so this slide is just to kind of now show you what microfluidic devices look like. So we have this laminar flow that you can see in the device on the left and the far right. So fluid, because it's laminar, is just flowing in one direction and it doesn't mix by turbulence. And this video in the middle from the Fulch lab in America basically shows this very nicely. Hopefully I turn the sound off because it's really horrible. But you can see that as they inject the different fluids, that they just line up in the channel in multilaminar flow streams, and they don't do any chaotic mixing. And it means that we can control this fluid very easily, and we can direct it in the microfluidic devices. So we have this high spatial and temporal control over the fluid when we're talking about microfluidics. So flow in microfluidics is highly predictable and controllable. It can be easily manipulated just by channel design or apply flow rate. And mixing is diffusion limited, so it means we have greater control over the reactions. We can really set a time 0 for the start of a reaction. Okay. Going back to the idea of diffusion, we do have to consider how quickly molecules diffuse within microfluidic devices, because we want to have control over that mixing. And this is just to really show you how diffusion works in microfluidic devices. So this is a multilaminar flow device. It's got 5 inlets with alternating ink and water. So you can see the layering in that device. It looks like there's no mixing involved in there. Sorry, looks like there's no mixing involved in there. But actually, if we change the dye out for basically liquids that do react together to give a coloured product, such as iron thiocyanate. So thiocyanate and iron by itself are colourless, but when they mix together, they form this blood red iron thiocyanate product. So we can see where the mixing is happening in that device, and it's happening laterally to flow. So you can see the red bands at the beginning of the device where the flow is just coming in is minimal, but towards the end of the device, it's had time to diffuse a little bit and mix together. But you can control that diffusion by increasing the flow rate, so it doesn't spend as long of time in the device, so it doesn't diffuse as far. Or if you want to induce diffusion or mixing, you can slow the flow rate right down as well. So we have a lot of control over that. Okay, so applications of microfluidic devices. One of the big areas of microfluidic devices is something called droplet microfluidics, and it's by far the most popular type of microfluidics that people use. It's this idea of being able to create droplets of water in oil or oil in water in microfluidic devices using something called a flow focusing geometry. And this is the geometry that you can see. I finally found my highlighter, that you can see in this video here. And we've got water coming through the middle, and then we've got oil flowing down the outside. There's a little nozzle here that pinches off droplets one by one. And as you can see, what's happening in here is just the change in flow rate changes the size of the droplet that you're making. And if you're very good with your fluidics, you can produce very monodispersed droplets. And the idea is that these droplets themselves can be, let's go back. These droplets themselves can be miniaturized or tiny little reaction vessels. So not only does microfluidics miniaturize reactions down to the size of a microchannel, if you make droplets within those microchannels, you can have tiny little reaction vessels that are even smaller. So you've got much more control over the reaction if it's happening in a droplet. And also, if you're making 1 million or even 1 billion droplets, you're parallelizing your reaction 1 billion times, which is impossible on the benchtop. So this is why droplet microfluidics is really one of the most popular areas, because you can do your reactions inside droplets, and you have an enormous amount of control over that reaction. You can manipulate small volumes of liquid with very high precision. And actually this video here by the Andrew de Mello's group from ETH Zurich really shows how quickly mixing occurs in droplets and how uniform the mixing is. So if you imagine you wanted to do this reaction in a droplet, and you really wanted it to start at time 0, if you're doing some sort of reaction that involves kinetics, then the way it mixes every time allows you to set that time 0 for every droplet that you're doing. And you might be doing 1,000 droplets or 1 million droplets. So and that's the sort of control you'd never be able to get without microfluidics. And these other ones are just examples of being able to do things like serial dilutions from this de Mello group one again. So a set volume, this is your reagent, and you have a set volume droplet hitting it every time. So it serially dilutes this droplet every time that happens, that collision happens. Here in this video, we're encapsulating single cells within a droplet, so we can do some biochemistry or genetic analysis on single cells by encapsulating them in a single droplet. So these are just examples. They're all very similar. This is another gradient generator device, just by being able to manipulate these very, very small volumes of liquid. Okay, so I was trying to think of an application that would resonate with you, having done nanotechnology, and I think Dr. Critchley probably spoke about quantum dots when he spoke to you. So you know that quantum dots, the colour that they give off or their emission depends on the precise size of that particle. So all to do with the band gap in that particle. So smaller particles tend to have a blue shift and large particles a red shift. But if you want to have a specific emission, then you need to be able to tailor the size of your nanoparticle very much. Droplet microfluidics allows for that highly controlled synthesis of quantum dots that is very, very hard to do in the laboratory on the large scale. So obviously people can do it, but you tend to have to be, your reaction has to be very precise. The person doing it has to be really understand what they're doing in terms of the chemistry and the reaction. And then you often have to do some sort of purification to get the size that you want out. And often or not, when you do it one day, it doesn't quite work the same the next. But doing it in droplet microfluidics allows you to have that high control every time. And this is just an example of a droplet generating device in which they're making quantum dots. And because they can control the size of the quantum dots so precisely, they just dial in what size quantum dot or what color quantum dot they want. And you can adjust the microfluidics, the droplet size, to be able to produce the nanoparticle of that size. So this is a really nice application of droplet microfluidics and just shows you the control that you can have over that size. Another huge area for microfluidics is in blood analysis, so this point of care diagnostics. And I just really wanted to show how they're integrating microfluidics with existing technology. So this is just a CD, so what we all used to have before we had Spotify. And on this CD, they've fabricated a microfluidic device. And when you spin it in a typical CD player, the centrifugal force is what drives the liquid around all these channels. And they've designed it in such a way that the resistance in certain channels directs the liquid into reaction compartments, and they can do blood analysis on a very, very large scale on a single device, just using the idea of spinning the microfluidic device and using the centrifugal force to push the liquid through different compartments. And then they've taken out the laser as such and put in an optical detection system, which means they get a readout from that analysis very, very quickly, a few minutes compared to a typical ELISA system that would do blood analysis that might take several hours. So really, really pushing the clinical diagnostics to higher advancement here. So fully automated detection of biomarkers in the blood in a fraction of the time of conventional labs. And I didn't say, but it only requires a very, very small amount of patient blood. So only a few microliters, a pinprick of blood rather than several milliliters. Okay, so now moving on to research at Leeds. So this is where I get to talk about what we do and how we managed to do it using microfluidic devices. And I don't know if it's particularly known, but we're very, in the NMP group, the molecular and nanoscale physics group, there is a strong drive towards cancer research, both in therapeutics and in diagnostics. So one of the things that we've been doing is using microfluidic devices to measure the mechanical properties of single cells. And why we're interested in this is because solid tumours in the body tend to have very rigid cells, but when they start to metastasize, so when they start to spread to other sites in the body, they become softer, so they can squeeze through tissue junctions and through the heart valves and things like that, so they can find secondary sites to grow. So this metastases would like to be able to detect the stage at which this cancer is at. And we use something called deformation cytometry in order to squeeze the cells using fluid flow and see how soft or how rigid they are. So this is a single cancer cell flowing into the center of this microfluidic device, and it's getting squashed. And we measure how much it's being deformed to be able to decide whether it's a metastatic cell or solid tumor cell. And we do this simply by manipulating the flow and the viscosity of the fluid. So if you have your inlet here and your inlet here, the fluid drives into this central point and stagnates because it essentially hits each other before it exits out of the outlet channels that you see here. And as a cell flows in, it becomes trapped in this stagnation point for a very short period of time, where it experiences compressive force from the hydrodynamic flow flowing down these channels and into this central region, but then also a shear force as it's stretched by the liquid that goes around this corner and back up the outlet channel. So it experiences two forces, both a compressional force from the fluid and a shear force from the viscosity of the fluid. And we can see how cells deform under these different regimes to give us an idea of the internal environment of that cell and whether or what stage it is in a metastatic cascade. So we tend to, we can control the compression shear force by changing fluid viscosity and flow rate. So in an inertial regime, we tend to have high flow rates, higher Reynolds number, but low viscosity fluid. So it's experiencing that compressional force more than it is the shear force. In a shear regime, we slow the flow rate down, but we use a high viscosity fluid, and that tends to bring that Reynolds number right down. And then it means that the cell is experiencing a shear force rather than a compressional force. They always experience both, but it's just the ratios that we're interested in. And different cell types have different mechanical properties that can be investigated using these. So for instance, this video here, if it will play, is a leukemia cell. Now, leukemia cells are a blood cancer, so they tend to be very soft because they've got to be able to travel around the vasculature system. And as you can see, they compress quite easily in that stagnation point when they flow in there. HT29 cells are a solid tumor cell, so they are a rigid cell. And as you can see, they deform very little when they come into this stagnation point into the center of the channel. Okay, and if we do some image analysis on how much those cells deform, we can actually apply a model to be able to extract parameters such as the Young's modulus from those cells. And we just use a simple spring and dash plot model. We have a sine wave for the velocity of that actual cell as it comes into the stagnation point. And from that, we can estimate the strain that that cell is actually experiencing as it's going through that stagnation point. And if we can apply this kind of combined Kevin Voigt model as well as an oscillating force onto that cell, and we are able to get out several parameters such as the maximum strain and the Young's modulus for each of these cells. And what we're also interested in, which is very hard to get when you're using other mechanical techniques, is this relaxation time. So how long, once the cell has had its maximum strain, how long it takes to actually relax back into its original shape. And what we find is some cells actually don't. So there's some plasticity in cells as well. Anyway, so once we can get these numerical values out for the Young's modulus and the maximum strain, then we can plot these to determine the type of cells that we're looking at. So whether it's a solid tumor cell or a blood type. So we've got the HL60 here is the blood cell, but here we've got two examples of solid tumor cells. And as we can see, we have a higher Young's modulus for the SW480s and a high Young's modulus for the SW620s, but this cell type is actually starting to be metastatic. So it's starting to soften again towards what a blood cell might be. So we can really characterize these cells using this technique. So the last few slides, I'm going to talk more about I'm involved in that research on single cell analysis, but my specific area is something called organ on chip. And this is a new branch of microfluidics that allows us to do tissue culture inside microfluidics in a way that you cannot do in conventional cell culture in a petri dish or a flask. So it's about tissue engineering on chips, so growing tissues, organs and diseases in a microfluidic device. And it allows us to model what we call the physical microenvironment of the body inside these devices, which you cannot do in conventional tissue culture. This makes them better test beds for new drugs and understanding disease. So if you grow cells in a monolayer in a petri dish or in a flask, you don't have any of the hydraulic components of being in the body, so blood flow, lymphatic drainage. You don't have any of the forces associated with shear stress or forces from other cells in a 3D environment. So you neglect all these parameters, which are actually extremely important in drug resistance and also disease progression. They're all neglected in conventional cell culture. So microfluidics is allowing us to model disease better. And also the idea of reducing animal models, so not using as many animal models in research. So what we want to do is take microfluidics and apply it to, for us, specifically to cancer. So modeling cancer on a chip. This is pushing towards, I just put this little bit in, towards the idea of being able to grow multiple tissues on a single device that represent different organs in the body. So when you're doing toxicity assays, so say you're applying a chemotherapy agent to a tumor in one area of your chip, you can have a kidney or a liver model in another area that you can then directly see the effect that it would have downstream on that organ, putting these drugs in the body. So that's what everybody would like to get to, is doing this organ on chip where you have all components of the human body on a single device in order to do your drug testing. So one of the areas that we looked at was being able to grow spheroids and culture them in a microfluidic device in order to do drug testing. So what we have here is microtumors or spheroids of colorectal cancer tumors with the associated fibroblasts growing. What we do is we grow them off chip, but then we introduce them into this microfluidic device that has little traps that then trap the spheroids when we flush them into the device and hold them in place. And this allows us to apply capillary-like flow rates over the tumours like they would experience in the body that you wouldn't be able to do in a Petri dish. So the chamber flow rates are between 0.2 and 0.8 microliters per second, which is equivalent to what you would expect in vivo. And also it allows us to introduce drugs into the system and test drugs on individual microtumors in parallel with each other. So you're doing multiple experiments on a single device as such. What we actually wanted to use this device for was to test. I have no idea whether you are familiar with microbubbles through Dr. Radwa or not, but I will give a little bit of an introduction. So microbubbles are small bubbles of gas that, when burst in the presence of a cell, can puncture holes in the cell membrane. And we've been using this for 10 years to see if we can enhance the delivery of drugs to cancer cells by having them in the presence of a microbubble and bursting them with an ultrasound pulse. So we wanted to use this spheroid array to see if we could prove that microbubbles enhance drug delivery to cancer cells. And just aside here, we also make our microbubbles with microfluidic devices. So not just the organ-on-chip work, but we use fluidics to produce billions and billions of very tiny microbubbles for therapeutic reasons. Okay, so this is just an image of the device. So this is the chip that you see down here. These reservoirs of fluid are what flows into the device, delivering all the media and oxygen to the cells so they can live quite happily in the microfluidic device. This is just a schematic of the side of the channel. So this is the ultrasound transducer we would then use to burst the bubbles when we put them in the device. And this image you see here is actually just a video, and you have to look very close. Oh, is it not going to play maybe? Just a second. We'll turn that off. There we go. So you can see the movement probably of something in the device around these colorectal cancer microtumors, and what they actually are tiny little microbubbles that we've injected into the system alongside the drug. And then we apply the ultrasound and burst the bubbles and see what happens essentially. So this is an example of one of the microtumors in Brightfield. DOX is the drug that we are delivering to them, and then we use a dead stain to see basically how many of those cancer cells have we managed to kill. So at the beginning, what you can see is a nice rigid circular spheroid, all intact, very happy, and you can see the accumulation of DOX in that spheroid on the outside of that spheroid. And at the moment, there's not much death because it's the beginning of the experiment. However, when we apply the ultrasound and burst the bubbles and then look 48 hours after we've done that, you can see that the spheroid has broken apart because the cells have died and the cell-cell interactions have been disrupted. You can see that the DOX has managed to get into the very center of that cell mass, which is actually quite difficult to do usually. And then when you look at the dead stain, you can see that the majority of that spheroid is actually being killed by the DOX. So spheroids decrease in structural integrity. They have a high accumulation of DOX in the spheroids, and this red stain shows high levels of cell death after that exposure to microbubbles and DOX. If we look at that quantitatively, we can see that if we just expose the spheroids to DOX only without any microbubbles, then they still tend to be about 80% viable to these spheroids, so only about 20% or more, it's 25% have died. If we put DOX in there and just do the ultrasound, so no microbubbles, then we do get more cell death associated with that ultrasound, so maybe 40% of the cells die. But if we combine the two, so the DOX with the microbubbles and the ultrasound, as you can see, we get a much higher cell death in the presence of all three. So that essentially shows that the exposure of spheroids to DOX and microbubbles with ultrasound significantly decreases cell viability. So it supports our theory that therapeutic microbubbles are a route to improving cancer treatment. The other thing that we're working on, this is very new, is what we're interested in, because not in tumours, you don't just have the tumour, you have the associated vasculature, so the blood vessels that are supplying that tumour with all the nutrients. And actually that is what the microbubbles will flow down ultimately in the end. So what we're actually doing now is we're growing microvasculature on chip, in order to study those drug-vessel interactions. So we're going to put microbubbles down these vessels. It's something we've just managed to do recently, and use the ultrasound and see what actually happens in the vasculature when we destroy the bubbles. Where does the drug go when these bubbles burst? So this is very, very new work out of Leeds, out of my group, and would absolutely not be possible without the application of microfluidic devices. Just recently, just for your information, NASA have announced that they will be taking organ on chip into space. So it's actually a fantastic way for them to test the effect of space and gravity or lack of gravity on tissues and cells without compromising human beings or animals. So they grow tissues and cells on a microfluidic device, take the device up into space, be able to do more rigorous testing and see how that affects the tissues and cells in the device. So NASA have now become very interested in organ on chip as well. Okay, so just a few acknowledgements just for the work from Leeds mainly. So these are the combined groups of my own, so the Peyman group and the microbubble group that we have at Leeds, and a few sponsors and some social media if you want to follow any of the research that's going on. And that's it. So I'm happy to answer any questions. Sorry about the glitch at the beginning. I think that should, yeah, stop sharing my screen now. So happy to take any questions.
Thank you very much. It was really great. And I can see we already have a hand raised, the first question. So Dr. Reem, would you like to start?
Yes, sure. Thank you very much. It's a very interesting talk. Actually, it's fantastic. I have two questions. I'm not a specialist in microfluidics, but it was interesting. The talk was interesting to initiate many questions for my scientific curiosity. One of them is that in the very close spaces between different chemicals in the reactions, how to avoid the signals that might overlap or interfere with each other because of anything like, for example, in flow cytometry, we have to take care not to overlap the signals of the fluorophores used, for example. The second question is about the cancer, and it's very, very interesting, really. So you mentioned that the solid tumor will behave differently than the fluid tumors, like the leukemias, for example. And it's it's very interesting to know that this has a cellular base. My question is, did you find in the same type of tumor, like for example, leukemia versus another leukemia, of the same pathological classification, but we know that cancers are very heterogeneous, and patients actually can behave totally different, whether in the aggressiveness or their behavior to response to therapy or things like that. So can you think of the cells from these different patients to be behaving differently in their way of deformity, in the way to access to metastasis location, to be this as explanation for the heterogeneous behavior of the same type of tumor, but in patients with different outcomes or different prognoses. So these are my questions.
Yeah, I mean,
thank you very much.
So in answer to your first question about having spatially very close signals and being able to differentiate between them, I think that's what you're asking. So you can, what people tend to do if they need to be able to separate two signals out, you know, from two droplets, for instance, is you can easily manipulate the flow so that you force the droplets to become further apart if they're moving down a channel. So those images that I showed of all the droplets all very, very close together is more just to show how uniform the droplets are and how they're so uniform, they stack very nicely together. So if you're actually doing an analysis and you didn't want any signals to overlap, you could quite easily manipulate the flow so the droplets were further apart as they were traveling down the channel.
Mm-hmm. Okay.
in terms of your very good question, and a question I think a lot of cancer biologists are interested in, but to give myself, kind of a bit of breathing space, I'm not a cancer biologist, but the heterogeneity you talk about is definitely something we see. I mean, we don't work with patient samples at the moment because it's still very much fundamental research. Mm-hmm. We do look at different cells within the same cell line, and even then we see that essentially from the same cell originally, we do see heterogeneity there as well. And I think I've been doing a lot of work on tumor mechanics recently, and the one thing that becomes apparent is that the cell's phenotype changes immensely just due to its local environment. So this is forces experiencing from other cells, forces it experiences from compression from growing in such a tight, dense area, the force it gets from interstitial pressure, so the way that water is held in tumours and creates an enormous pressure in there. And then on top of that, they change depending on how many nutrients they're getting, how much oxygen they're getting. So cells in the centre, as you probably may well know, they become hypoxic, and they actually, that drives metastasis, so it drives the softening of some cells. And I think you get such difference between patient and patient, and this is just my interpretation, because probably those local environments are just so different all the time as well. That the tumour is very specific to the patient, and therefore the phenotypes of those cells within the tumour are also very specific to the patient. And what we'd really want to do ultimately in the end is to take samples from patients and do the analysis on those, so your results are always patient specific. In terms of the internal structure, what we tend to find is that the softer cells don't have as advanced actin and microtubule cytoskeletons as some of the more rigid ones. But what drives that and what makes it so different from patient to patient is just a guess of mine related to the microenvironment.
Right. Yeah, it's very actually truthful answers, and it answered my inquiry. And I might add that having patient samples, actual patient samples, will be very informative. Things like the microbiota, for example, it's totally different niche from one patient to the other, and it will affect the leakages of blood vessels and the tight junctions between cells. All these might explain, together with the nature of the cancer, will explain the aggressiveness or the being metastasizing or not. So yeah, it's
I think so. Yeah, very definitely.
Yeah. Okay, thank you very much. Thank you.
Thanks a lot. I can actually see that I think we have succeeded in saying that this is multidisciplinary science. So you have showed this clearly in your talk, Sal, joining or showing comparisons between chemistry and physics and how are they similar to each other, and now introducing biology as well. So I can see this also in the diversity of questions because, for example, so Dr. Reem was a medic, but now we have another question from a chemist, and I think we have another question from a biochemist. So it's a sort of wide range of questions, and you will have to answer all of these, by the way. So now we have Dr. Ahmed, would you like to ask your question? There you go.
Yeah, thanks, Dr. Radwa, and thanks, Dr. Saleh, for the nice talk. So it was really very interesting. So even though I'm not a specialist in the microfluidics, but the applications are very, very interesting, actually, especially the one related to mixing the liquids together to form, for example, some emulsions or something. Actually, this is a part of my major. So my question is related to this arrangement of droplets. How did you avoid the coalescence between these droplets? This is first one. And how about the large scale synthesis? So can we, for example, use it to synthesize a large scale? The last one, can we mix some like stabilizer to like make that kind of emulsions more stable? Or we don't need, just mix the two phases without any stabilizers?
Yeah, okay, so I think question one's probably related to question 3 as well. So yeah, you do have to.
Sal, I think you will like to answer question 1 a lot. You have been asked this one a lot about the coalescence of cells or sorry, of droplets or whatever.
So yes, if you're using water in oil, then you have a high surface tension, and as soon as those droplets touch each other, they will coalesce. And the same is for our bubbles, for instance. If we just used gas in water, extremely high surface tension and likely to coalesce when they touch each other. So what we do is we use a surfactant to stabilize those droplets. So if you're using something, doing it for non-biological reasons, then you can just use, any kind of surfactant to basically lower that surface tension and allow the droplets to exist as a single droplet. For the microbubbles, because we ultimately have a biological application for them, we tend to use lipids. So we coat the surface in a lipid to stabilize those droplets and allow them to be, as you saw in that picture, to be able to touch each other. Does that answer the question?
Yeah, actually, yeah. As for surfactant, they may be soluble in one phase, but how about using some nanoparticles which are insoluble, but it's dispersible? Is it same?
Yes, you can do. Yeah. I've forgotten Pickering emulsions.
Yes, so, yes, Pickering. Yes.
Yeah, you can use nanoparticles as well, as long as they will self-assemble on that either gas water or oil water interface. Then people do use them to stabilize. What you just tend to need, and this is probably a limitation, is that the formation of these droplets happens so quickly. You do need the whatever you're using to stabilize that interface, you need it to be able to diffuse very quickly, to be able to coat the droplet as it's been formed. If you have something that has a very low diffusivity, you might get problems that it's not quite, your droplet is not quite coated in time before it leaves the device. But that's the only thing. Otherwise, people do use nanoparticles as well. Yeah.
Yeah, and this is, for how long does it stability with time? For how long?
I mean, it depends on the phase that you've made, and it depends on the surfactant. I know people who make, well, we make liquid crystal droplets. They're stable for weeks and weeks and weeks. Our microbubbles, on the other hand, not quite as stable as that. We have increased the stability a lot, but they wouldn't last as long as that. So it very much depends on what you're making and what you're stabilizing it with.
Yeah, and how about the large scale senses? The last question.
So yeah, that is a very good question, because obviously, I've just talked about only microliter volumes of liquid. What you would do is paralyze the actual devices. So you put many of those devices on a single kind of chip. So that's how you would scale it up. So you would use more volume, obviously, but it's because you want to produce more nanoparticles or more droplets. So you would take that single device that I showed and you would scale it right up. You would paralyze it on a single device.
Okay. Thank you so much thank you.
That's okay.
Thanks a lot. So we have another question from Dr. Dina. Would you like to start?
Yes. I'd like to thank you, Sally, for your nice talk. It's very interesting. My question is, with the organ-on-chip model you suggested, are you able to validate or dissect, for example, signal transduction associated with a specific type of cancer? This is my first question. And my second question, would it be possible to remodeling the behavior of cancer cells to reprogram them to switch to different behavior? On this model, for example, can you reprogram certain malignant behavior, such as epithelial to mesenchymal transition to the reverse?
Yeah, very, very, very good questions. Thank you very much. So it enabled to measure signals in the cells. It depends on two things. One, if you need to be able to take the cell out of the device and do some analysis on it afterwards, it is possible to do that. So we do all our quantitative analysis, our sort of ATP assays that we do on the cells. We take the cells out and then mulch them all up and do that conventionally. But if it's just something it's secreting into its environment, the nice thing about microfluidics, because you've got constant flow, is that you can just collect the liquid that's coming off the chip and analyze that for the signal molecules that you're interested in. So you can measure in situ what cells are secreting or the signaling molecules they're producing without having to disturb the culture. So it is possible to do that. And then the second question, which is a brilliant question, is yes, you can. I don't do personally, but a lot of people do study the EMT, the transition, because they can change the environment and change the kind of cues that tell cells to behave in a certain way. So, and there's a lot of study on stem cells, in particular in microfluidic devices, because you have such control over their environment that you can persuade them to go down one differentiation path compared to another. As I say, we don't do that personally, just because we're only really 3 years old in my group. But people do that, so it is possible in microfluidic devices. Yeah.
Yeah, promising. Thank you.
Yeah, thank you.
Oh, thanks a lot. And I think we have our last question now from Dr. Hassan. Would you like to go on?
Yeah. Hi, Sally.
Hi.
Hi, how are you? Thank you very much.
Thank you.
It's actually a very interesting seminar or webinar, and it's expected from you, Sal. I'm aware with a lot of this work, and my question here is actually going to take you out of of this application to the current pandemic, which is the COVID. Mm-hmm. I know COVID can cause clots, and I'm not sure if you can actually add something to the bubbles, like anticoagulant, and injected the bubble to the lung or somewhere to the where the clot is. And actually use ultrasonic or something to disrupt this one. It's this is something just crossed my mind now, and because everybody now working on COVID and try to find solution, to find medication. I know COVID is very rapid, right? And people try to find a quick solution or quick actually treatment, and I don't know if bubbles can help in actually solving such problem.
I mean, for certain, so a lot of cardiovascular disease could be treated with bubbles. You can deliver almost anything with a bubble, as long as it's water soluble. Well, we can deliver hydrophobic drugs as well. So the delivery is not a problem. What I envisage being a problem, and you've just found that the only weakness in bubbles is we rely on that gas liquid interface for the ultrasound. So to burst the bubbles, it's the interaction of the bubble with the ultrasound which is dependent on its basically the gas liquid interface. And in the lungs, that's the one place that we would struggle to get the ultrasound in, because you'd have so much reflection from the gas in the lungs that we might struggle to burst bubbles in the lungs. And that's about, I mean, I've worked for 10 years on this project with Dr. Radwa, and she'd probably be nodding right now that the lungs is the only place we're going to be limited because of the air in the lungs and getting the ultrasound to the bubbles. But in theory, you can deliver, you know, in the body anywhere but the lungs, most things with a microbubble. So I hope that answers your question.
Right. Yes. Right. Okay. Thanks, Sally, and we are looking forward to more actually seminars or collaboration with Galala University, and specifically probably with Radwa on the nanotechnology side.
Brilliant.
And, yeah, and looking forward to see you face to face, Sally. Yeah.
Yes, that would be nice. Thank you.
Yeah.
I guess I can't see any more questions at the meantime, so I think we are coming toward the end of this seminar. So thanks a lot for your time, Sal. Thanks a lot also for everyone who attended. Hope that was helpful. It was a pleasure having you with us, and it was really exciting to have such a nice webinar, which is actually collecting all types of science together, biology, physics, chemistry, cancer biology, all of these things, fluid dynamics, all of these wide scale terminology. So that's great. Thanks again, Sal, and we'll be looking forward to meet you maybe in Leeds or something at some point.
Thanks
Okay.
for inviting me.
Right,
Thank you so much.
Kalala, yeah.
Thank you.
Thanks a lot.
Thank you.
Right.
Okay, bye.
Thanks.
That's it.
Thank
Thank
you.
you. Bye.